All right, this is lesson 13.3.2. How fast are you going right now? Instantaneous velocity. So we're going to continue our work with position velocity graphs to make a connection between velocity, position, and the slope. We're going to calculate instantaneous rates of change to create slope graphs. Okay, so just going to take you through this without necessarily a resource page. And this is like a demonstration, right? But I'm not going to use that one. So here's the idea, okay? The speed, and this is important, right? Speed is the absolute value of velocity. And so the way I explain this is, if we get in a car and we travel down the road, say, okay, we're going 50 miles an hour, that's our velocity, okay? As long as it has direction. So those of you that have taken physics, you have a direction. I'm driving north at 50 miles an hour. That's your velocity. Okay, if I turn around and drive back south, home, wherever that is, right, that would be a negative 50 miles an hour in velocity terms because I'm going in a negative direction, okay, from where I started. In my car, it's just going to read speed, right? And speed is absolute value. It means it's always positive, okay? So that's kind of an idea there, right? Looking at the next one, we have just some scenarios here. So you walk quickly from the start for 10 seconds, you stop for 10 seconds, and you walk slowly towards the start. So here's this graph, right? So we walk away from the start, right, quickly for 10 seconds. We stop for 10 seconds, and then we walk slowly back towards the start for 10 seconds. Okay. So that would be your position graph, right? Your velocity graph. Right, is a positive velocity quickly, right? A 0 and then a negative velocity, but not as much of a negative value as this one. So let's say this is like 10. This would be like, negative 2. Okay. So it's not as, we're walking back not as quickly, right? Okay. So looking at that, looking at 112 here, just so you get the idea, the velocity graph is generated from the slopes, right? So this was a slope of 10 over 1. This would be a slope of negative 2 over 1, right? It's generated from getting the slopes of these to get your velocity, right? So use your work from 117 to answer the following. What types of functions best describe position graphs? Linear functions, right? What types of functions best describe velocity graphs? Constant functions, okay? Why does it make sense to call a velocity graph the slope graph? Why? Because it is made from slope, right? Velocity is a rate of change, and so velocity is a rate of change, and slope is a rate of change. So that's where that comes from. Okay. Looking at the next one here, 113. At this point, it's natural to wonder about slope graphs, right? Each student be assigned a different X value. So here's the thing, right? If you're looking at slopes, right? What's the slope if you have a constant, right? That function looks like this, right? It's a horizontal line at 3. Well, what's its slope? It's 0. Okay, so a constant goes to 0. Okay, look at the next one. F of x equals x, right? That graph looks like this, right? Sorry. Right? And it has a slope of 1. So a linear goes to a constant. Okay, look at f of x equals x squared. So hopefully we're starting to see a pattern here, right? And if you have x squared, guess what its slope is? x, right? It changes every time, but it's increasing, right, in a linear manner. So hopefully we see this pattern. Guess what x cubed's slope function's going to be? It's x squared, right? There's more to it than that. There's a constant that goes to the front. And you'll learn this in calculus of how this works. Okay, but you get the idea. It should go down. Like your degree should go down to your slope. 3 goes to 2, 2 goes to 1, 1 goes to a constant goes to 0. Okay, and that is lesson 13.3.2.